Appreciate the introduction, and I just want to second that we're super excited to have everybody here. We're really, happy to be able to continue this tradition that we started last year, and we're looking forward to another great show today. And without further ado, I'll kick it off. So the title of my presentation, as Steve alluded to, is A New Compute Normal. And I turn my clicker on. This actually came to me, so every year, toward the end of the year, my friend who runs this publication called VM Blog, it's one of the premier server-based computing publications, asked us for predictions, for the next year. So, and it's not just me, it's pretty much everybody, all my peers in the industry. But basically this year, last year I thought long and hard about it, and I thought, you know what? I really think that, based on what we're seeing, that 2017 is going to be the year where we stop referring to accelerated compute as accelerated compute, and it's really just becomes compute. And we'll get into why and kind of go through it, but I actually think that's a profound inflection point for our industry, and we'll kind of go through some of the history and all that, and we'll see why. So what's driving accelerated compute? So first is kind of the end of Moore's law for CPUs. So actually Steve's keynote from last year was about how Moore's law for CPUs is, and this is well accepted in the industry. So you're not going to continue to scale your application on CPU only. You're going to need to be able to produce the kind of applications that are going to really drive innovation, machine learning, all these different things. You're going to need some computational accelerators boosting the CPU to do the work that needs to be done. So otherwise, you just can't rely on continuing to double performance every 2 years, just as it's been law for the last 40 years. Power density, so what we see with the efficiency that we can get out of dedicated sort of co-processors and accelerators for specific things, right? I mean, they can't do everything, and that's the reason why CPUs aren't going away anytime soon. I would think never going away. But there are specific things that accelerators can do, and do very, very quickly and very with good power efficiency that really kind of highlight the benefit of specialized operations versus general purpose operations, which is what you get with CPUs. Software algorithms are evolving to obviously start to take advantage of and assuming the presence of accelerators of different types. There's also maturation of toolkits above the actual the kind of the assembly language or the machine language of the accelerators. So we see things like OpenCL, like CUDA, and other toolkits that enable us to write high-level code. Well, we would consider it to be high-level code. Not everybody. Some people might still have a bit of an issue with the complexity around it. But then there are frameworks on top of that take advantage of CUDA, like machine learning frameworks and all these different things that allow you to write really high-level code on top of these accelerators. So there's a lot of maturation happening in that space. And again, we're burying kind of the implicit assumption that this compute is available and let's just use it because it really makes things a lot more efficient. I'm assuming everybody here knows that deep learning is one of the hottest things that's ever happened to accelerated computing, and it's super hot right now and really driving. It's really difficult to do deep learning at any sort of scale or performance without acceleration, and we'll get into that a little bit more. But the one thing I really want to focus on is how data has evolved over the last 40, 50 years. And really, to me, everything kind of comes back to the data that's being processed and how it's being processed. Otherwise, there's no reason for compute if you don't have data to actually work on or produce. So if we think about kind of the modern age of data and computing, we'll start in the 1970s when relational databases really started to emerge. Before that, it's not that we've had data for millennia. We've been recording data, but in computer systems, data was very much a monolithic tool of an application. So it didn't actually have a life of its own. But then in the 1970s, we started seeing, okay, well, look, we can organize the data, manipulate it, and make it available to different applications and provide different views on it. So really the focus, you didn't have to go to a different terminal to access a different database now. It was basically, now it was its own entity. And now the focus became around data management, things like capturing data, organizing data, and then searching for data. These are things that we really worked long and hard for in the 70s, the 80s, and even the 90s on how to really optimize kind of normalize data in databases, index them, all these different things that we kind of take for granted today, but are still really important, but they're kind of, those problems have been solved, right? And even though a lot of times we still screw up when designing, kind of data backends, for the most part, we know what to do now. It's no longer kind of figuring out how to deal with data. So really the 2000s, once all that really matured, the 2000s became the era that I'll refer to as big data as one of the most overused terms. Actually, I think deep learning will surpass big data in terms of the most sort of trite terms in computing, but a lot of people still throw big data around for just about anything that involves data. So as we know, big data is not about the size of the data sets, but the types of processing that we do on the data. So we can no longer do traditional sort of indexing and searching. Now it's all about analytics. And that's really what defines big data. A giant database is not necessarily big data, but what you do with the data, it makes it big data. So a couple of, so again, the era of data analysis kind of emerged, right? So it's really about, okay, don't just tell me what's in the data, describe it. Tell me what I can learn from the data, right? And by the way, let's not worry so much about structuring it because it's coming from all over the place. So instead of doing that, let's actually reduce it and then actually do analytics on it. So that was kind of a big break in the 2000s from what we had been doing before with data. So today we've moved into, again, I don't want to say we've perfected big data platforms, but they're mature enough that and the capabilities and kind of the problems we want to solve today are complex enough that we believe we've moved into the era of data science, which is all about accelerated cognitive computing. So when we were describing the 2000s, now we're prescribing. We're predicting. We're doing things like creating new processes automatically and then running analytics on those processes. In fact, we're at the point now where the algorithms actually tell us what questions to ask instead of us trying to figure out what we're going to ask the system. So we're learning things from data that we didn't even realize we wanted to learn before. And that's kind of the essence of a truly cognitive system, right? Something that begins to learn and hopefully not in the self-aware terminal human sense, but in the teach us what to learn sense, so that we can kind of augment our own cognitive skills with those machines. And the key here is that it's really created an insatiable thirst for accelerated computing. So if we look at, just to polish it a little bit more, how working with data has transformed through the eras, right? And when we started with, it was sorting and indexing were actually big challenges, right? And we take that totally for granted today, but actually sorting data used to be a pretty complex, and there's a lot of sort of computer science 101 things that people learn about how to bubble sorts and quick sorts and all that stuff, and that was all really relevant. Now it's completely abstracted. That stuff is, in some cases even built into the hardware. It's just no longer, critical to really understand. So we were basically indexing, querying. So today we're analyzing and predicting, right? Viewing, it has now become visualizing patterns, and what was once entity relationships is now unstructured relationships. So we used to be able to map everything out and draw these nice entity relationship diagrams and all these primary, foreign key things, and now it's like we just don't even know what the data's going to look like when it comes in. So how can I possibly predict how it's going to be related? And that's something that the analytic actually does, that before was actually done by the database engine itself, right? So naturally, the sort of jobs that are available around data are very different now. A lot of you in this room probably remember data entry operator was actually a career path. I mean, you could be hired to take a stack of paper and type it into a computer. Well, that still happens probably in government work, but realistically, most of the world's electronic now, and there's no shortage of data coming in, right? So now it's about analyzing what's actually coming in. So the business analyst and the data analyst is taking the place of the data entry operator. The database administrator, whose job it was to make sure that the data was actually indexed properly and accessible, is now about sort of architecting different data streams and trying to imagine the data engineer, data architect, trying to imagine how these things are going to coalesce with analytics versus kind of spending your entire life optimizing tables and indices and all these different things in a very static system, right? Which is now completely dynamic, changes all the time, and that's just kind of the nature of it. And then the application programmer who created the software that allowed people to interact with the data. You guys might remember, the explosion of 4GLs with, Power Builder and all these different things that were super hot technologies and really important. But now it's really about the data scientist. It's not, the application is kind of being defined at the time that you want to decide to analyze the data. It's no longer so critical to, have a pretty GUI to enter data into. Now it's about, let me write this analytic and get the answer, right? That's what the data scientist does. In short summary, what's happened is there were in the past, business was kind of structured around a set of people responsible for enabling the data platform for the business people to actually act on. Now there's no difference between the data people and the business people. It's literally, there are companies that are actually founded by data scientists now and are very successful. So it's really all about, the success of companies over time is going to be about who understands data the best. So this is no longer a separate function for kind of the engineers in the back room. Now it's just an integral part of the business. So it's no longer enablement, it's just kind of woven into the fabric of the business. So if we kind of, if we take kind of a trip down memory lane of what these systems look like throughout the ages, so obviously the database era was all about monolithic, static, centralized, and fault tolerant. So we could not afford any type of failure that was in any way visible to the application side, because that was an interruption of work, of business. In the big data days, we started distributing, scaling out. Obviously, performance became a big deal, because now we started spreading, this is no longer about optimizing a single system, but optimizing a cluster, optimizing the pipes coming into it, the streams coming into it, and all these different things that were kind of different than what was done in a database era. And now fault tolerance, and this is a bit of a nuance, it's functionally the same thing, but high availability and fault tolerance there are some nuances, right? It means that you can actually take a failure. You've designed your system to fail. So we did things like add a bunch of replication, add algorithms to distribute parity across different systems, et cetera, so that we could afford even a large number of failures in production without actually bringing the system down. And there's a certain level of service degradation that we're willing to accept as a result of that. This was all designed into the systems, right? From the hardware to the software. So again, the goal was fault tolerance in the sense that there wasn't going to be an interruption of service as a result of a failure, but we accepted that failure is inevitable and it's going to happen. And by the way, we're going to use cheaper components because we've already designed the system to fail, so we can afford to have failures and we'll just throw them away and replace them, right? That's kind of what happened versus the database era. And now in the data science era, it's really all about cloud, right? So it's about cloud in terms of the elasticity, but also the heterogeneity of the things we're looking at. For example, and we'll get into this more later, but if you're doing data processing, if you're actually doing a deep learning pipeline where you have training, first you have ingest of some sort, potentially your data platform, then you have training, and then you have inference or evaluation. There are different types of computational accelerators suited for those different steps of the workflow, but you're operating in the exact same problem space. So it's no longer just, let me go do my stuff over here and then transfer it over here to do this kind of processing. It's about the entire workflow. The input and the output is maybe flowing through 3 different types of systems transparently to the end user. And the best way, obviously, us being a heterogeneous cloud company, I'll tell you shamelessly that the best way to do this is in the cloud, because you don't actually have to go out and purchase all these things. You can use them on demand. And by the way, you don't have to upgrade them either. Cloud providers are on a much faster upgrade cycle than enterprises, right? I mean, we retire hardware much faster than the 3 to 5 year buying cycle that an enterprise buyer does. So you always have access to the latest and greatest. It's already deployed, it's already tested, and your software can just take advantage of it. But again, the very key is the acceleration. So there's a lot of analytics that you could do on big data platforms that are really about things that maybe didn't require acceleration to be fast, but for data science, for training a neural network, for doing these different things without accelerated compute. If you're trying to do the CPU only, you're looking at weeks instead of maybe hours of work, right? So it's very very key. So just to look at kind of the software technology, in the database it was all about application, client server, and then model view controller, which is still very relevant today. that's kind of the modern implementation of a database that's kind of replaced Clam server. In the big data era, we perfected distributed file systems, cluster computing and analytics. And in the data science, now we're looking at in-memory databases. Again, and I tell this story all the time. I paid like $600 for 128 megabytes of RAM 20 years ago. And now, you know what the memory prices are like, right? And we still think they're expensive, but we're talking about the amount of memory that can actually fit data sets, which was completely unheard of. Even a few years ago, is now available to us, and not just in systems, but on demand in the cloud. Right? We can get half a terabyte or even 1 terabyte systems on the Nimbix cloud for very straightforward on demand rate. Accelerated analytics and then frameworks. Right? That's kind of the thing that we started seeing in the big data era, but now it's all about frameworks, and there's so many of them, and there's so many iterations and new ones coming out all the time, and some of us don't necessarily think that's a great thing, but it's great to have choice and diversity, but it's really, it's going to be a while before we see any kind of real consolidation there, because there's so many new problem spaces that are coming out all the time. So what makes deep learning so suited for accelerators? Well, it's highly parallelizable vector and matrix operations. These are very simple instructions that are perfectly parallel. You can do thousands or millions or billions of them at the same time. And what you get from like specifically with the GPU, for instance, is you get thousands of cores instead of 16. Or maybe in a many core processor, maybe you have a few dozen cores. But again, you're looking at really just doing super simple arithmetic operations. You don't need CPU cores to do this on, right? So it's perfectly suited for this. And what ended up being a cosmic coincidence is the stuff that made our graphics really fast works really well for deep learning. This is the same types of operations, but instead of kind of rendering it on the screen, we're creating graphs in memory, right, to actually process them. So this is actually it's an extrapolation, I'll be honest, but it's a very common benchmark, and this is actually taking the ResNet 50 example that we have a lot of experience with benchmarking. And if you look at kind of the Pascal Titan X, which is the kind of the consumer version of the P100 that we have in the cloud, you can see the kind of speed up that you get where I don't know if everyone sees it, but the bottom is a dual Xeon 16-core CPU only setup that took basically 6.6 seconds to process a single iteration, and the fastest GPU took was 64 times faster than that. So if you actually extrapolated that out over say 1,000 iterations, and you're obviously running a lot more than a single iteration with these networks. You're looking at a 64x speed up at only a 32x price premium. So it is a 2x unit cost. Of course, it's more expensive. P100 is a really expensive GPU. And these numbers are actually based on Nimbix Cloud actual pricing, right? So this is not made up. But it's 64 times faster. So you pay double the unit cost, but you get your answer back 64 times faster. So just imagine, if time is money, imagine what that adds up to. And you don't have to imagine it that much, because even in the cloud, even if you have all the time in the world, you're paying 14 cents to do it on a GPU instead of almost $4.50 to do it on a CPU only. So in terms of straight arithmetic, it makes sense to use accelerated compute, right? And in time, it's less than 2 minutes versus almost 2 hours, right? So huge difference to do this. And this is actually, these numbers are real, right? So the good news is that it's not just deep learning that benefits from GPUs. This is just an example of different domains that provide turnkey GPU accelerated applications. A lot of these you can just run directly on the Nimbix cloud. Obviously, deep learning is a huge use case, but you can see even in simulation, even industries that were algorithms that are 40 years old. They're realizing that by accelerating them, you can get a 10x cost advantage in terms of overall solution cost, even though you're paying more for the actual hardware. So that's, and kind of in the era of utility computing and commodity cloud, where we think about sort of instance pricing, it's important to think about solution cost instead. It's how much it's going to cost me to solve my problem, not how much per hour is it going to cost to run this machine. that's completely irrelevant, right? So it's really important to put that in context, and we can see it could be orders of magnitude. It's not, even though you might be paying more for the unit, right? So it's really important to think about your total problem space when you're calculating that. So in short, anything interesting you can do today is just either depends on or greatly benefits from accelerated computing. So there's very few things on here that are not interesting to somebody. And there's very few things outside of this box that are as interesting as anything in this box. So that's that. So I like to think of myself as a bit of a historian when it comes to computing, because I've been around computing all my life. Steve mentioned my career and so forth, but I literally started when I was 3 years old. I had a computer at home and I started hacking on it. So it's my entire life has been attached to computing. So I like to kind of go down memory lane sometimes. But surely, this whole computational accelerator thing can't be new. I mean, history seems to repeat itself all the time, especially in computing. I mean, things that we think are new today are actually just incarnations of things that happened before. So let's go back to the future, right? This is 1989, and that's a camcorder, which the app that records video on your phone is actually that thing that went on your shoulder before. So if you had one of those, and they were not cheap, but if you had one of those, you're pretty cool, but not as cool as if you had one of these, right? The math coprocessor. This is state-of-the-art Intel x86 architecture in the late 80s, because you could not do floating point math very quickly on the central processor. You simply didn't have the instructions. So you were actually using an emulator, and of course, the tools that you used, Microsoft or Borderland or whoever's compilers, had emulated libraries for floating point, but they were hundreds of times slower to do like even double precision multiplication on that library versus doing an instruction on the 487. Now but the 487 was incredibly expensive, so that was kind of the trade-off. But this is very much a coprocessor setup. You could run the CPU without the math coprocessor, but it just gave you such a boost to be able to do that. That it became essential for scientific computing, right? So in the 90s, we figured it all out, right? I mean, we basically put the math coprocessor on the same chip, or the same die, as the CPU, and we made it so dense that we could actually put two of them now. This is pretty, commodity x86 architecture in the 90s. And by the way, it's kind of hard to see, but the copyright date on that Pentium is only 3 to 4 years. It's 92 and 93 versus 89 for the 486. So think about what Moore's Law was doing in those days, right? So in 4 years, we doubled the functionality of the processor, and we quadrupled the speed of it. So those days were great for CPU, right? But as we'll see, there's even bigger things now. So I guess my point is, why did we think of this in the 80s? Well, the answer is we didn't have the technology. But from the 90s forward, we didn't have to worry about at least in x86 architectures. We didn't have to worry about how are we going to do math quickly because the processor just simply does it, right? So today, and this is another sort of shameless plug on our Nimbix technology, but now it's all about heterogeneity across the board in terms of not just CPUs but also accelerators. Not just the brands or the technologies, but the sort of the fundamental types of accelerators that are available. I mean, we're looking at here two leading CPU architectures and 3 very different types of accelerators. That what's very key now is that you have to have software actually define the infrastructure for you, because again, if you're doing a heterogeneous workflow that involves different stages of a pipeline, the last thing you want to be able to have to do is like stop doing your work here and move over here to do your work, or even reconfigure the system, right? So JARVICE, which is actually our software platform, actually does this reconfiguration transparently for the end user. So you can actually move your workflow from CPU only to GPU accelerated to FPGA or many core accelerated without having to stop and go to a different system. It's the same API, the same images, everything, right? So the full circle and the new compute normal is that we're very much doing code processing. And I remember using this term, asking a semiconductor company employee about their code processor, and he said, "Oh, I haven't heard that in 30 years." It's true. It's a pretty ancient term, but it's literally what we're doing. We are central processing and co-processing. We're just doing that with, kind of much different and bigger architectures than we were doing before. So it's very much back, and it's staying with us for the foreseeable future. But now it's about choice and accelerators and enabling diverse workflows. And we know there's a healthy or unhealthy competition between sort of GPU technology and FPGA technology, and our point is that both of those are valid in different stages of a workflow. I mean, the FPGA is really good at certain things, the GPU is really good at other things, and there's no reason to have to kind of say, well, I'm only going to use this technology or that technology. Your software should be able to adapt, and your platform should be able to provision, what it is that you need. So, again, cloud is really fueling this. Not having to, go off and build these different architectures. You can very easily test your code, sometimes without modification, depending on the frameworks that you're using, on different architectures. And it's happening at a fraction of the cost as it was before. So, even if you do a lot of experimentation, if you're paying on-demand rates, you're probably paying, just pennies on the dollar versus buying what systems do, right? So, our point is that the new compute normal is accelerated compute, right? Let's just stop saying accelerated and just assume that compute is going to be accelerated from now on. So, what does that mean? It means that all complex algorithms should just assume the availability of accelerators. You should assume the architecture of accelerated compute underneath. You should not be writing an algorithm in 2017 that does math, or that does some sort of high bandwidth operation or whatever it might be, and not be thinking about what type of hardware am I going to run that on. You're no longer limited to either what's on your desktop or what's available at Fry's, right, or whatever. It's all about, if the FPGA is the right technology for this algorithm, then I'm going to write my OpenCL code to take advantage of it, right? And that's it. And it's not, and just assume that it exists. It's a given that access to accelerators exist, and the cloud is actually fueling all that. Because again, you don't have to buy these things, you can just consume. And then finally, computer systems heterogeneous at every level, so it's not just the nodes itself, but components within nodes are heterogeneous. And again, the example of the sort of, the pipeline, of a very straightforward deep learning pipeline, right? Kind of reduce the data, ingest the data, maybe do that CPU only, maybe use, a many core processor to help, whatever. Do your heavy training on GPUs with thousands of cores, and maybe you're using 64 P100s to do it on for that stage of the pipeline. But then your high frequency, the power efficient stuff, your high frequency inference, use the FPGA for that, right? And the beauty is that if you're using a technology that's enabled with a framework, it's the same Python code that you may have written actually works across all those technologies, without issue. Right? So as developers, how can we, force multiply computational accelerators? Because obviously hardware doesn't, kind of exist in the vacuum. It has to be consumed, and the average person, can't write Verilog or whatever. I mean, they have to be able to consume this stuff. So is it even our responsibility to do anything, right? So what is our responsibility as a community? And the answer is yes, it is our responsibility because programmable hardware exists to enable software. If it wasn't there to enable software, it wouldn't be programmable, right? I mean, if it's not programmable, it's something that just runs statically all the time, maybe it's an alarm clock or whatever. That's kind of the class of hardware that's not programmable. Everything else is designed to enable software so that we can reprogram it and use it for different purposes, right? So there's three things we can do. First, we can focus on serverless compute. Now, of course, and we want to make this be normal. Of course, there's no such thing as software in the cloud that doesn't run on servers. So it's kind of a marketing term, but it's really about how you present it to the end user, right? So it's about improving machine utilization by actually hiding the machine from the end user and just focusing on the problem they're trying to solve and putting an API around it or putting a graphic user interface around it. So in the example, if you're going to run an MNIST training on TensorFlow, just create a very straightforward user interface for that, where the user supplies the actual code. This is actually a screenshot of our user interface for TensorFlow. Versus have them spin up a server, SSH into it, run Python, and then remember to shut it down when they're done, right? There's no need to do that. Let's give the end users the experience that they deserve, and let's focus on serverless compute. The second thing is taking a less is more approach. We really like configurability as developers. We love it to the point where we will design ourselves into, into frenzies, trying to make sure that things are extensible. The reality is that extensibility matters more to developers than to end users. End users want the right choices, not all the choices. And that doesn't mean that you make things not configurable. It just means that you configure them out of the box to just work, right? And the example I use all the time, and I'm a Unix guy, like, to the bone, right? But the example I use is, this is why Microsoft was so successful in the software industry, is because if you wanted to actually send email, your email package just did that. If you tried to do that on Unix, you had to actually configure sendmail to send email. Well, that's actually what sendmail is for. But yet it required you to write a sendmail configuration file to even use it to send email, right? Why? Because you could also use sendmail for X, Y, and Z. But again, that basic use case that works out of the box, that satisfies the 80% of the end user, is the key to enabling advanced technology for end users, right? And let's not disable extensibility, but let's focus our extensibility efforts on the developer community and not the end user community. So one thing that's kind of very obvious is standard versus expert mode as well, right? So you'll look here, I know it's kind of hard to see, but there's kind of the sensible defaults for the mandatory parameters, and then here you have the optional ones that end user may not care about. But if you're a power user, you just go into that tab and you configure all the knobs and all these different things. But the end user that's solving the problem that maybe 80% of his peers are solving can just focus on the 3 or 4 questions they have to answer to get it solved. And there's sensible defaults for each one. Right? And the third thing that we need to, and this kind of is fundamental to kind of the previous 2 things, is science is not development, right? I talked to a scientist the other day who told me that 50% of the time scientists spend doing their work is actually fighting technology. And that's just completely wrong, right? Why? Why is that necessary? Just imagine what the world would be like if scientists were unleashed to do innovation and not even, the technology just works, it's a given, it just works, right? That's our role as developers. Let the scientists do the science, we can do the development. And by the way, computer science is science, obviously. I'm not saying it's not science, but let the biologists, let all these guys actually do their hard science and just assume that the code we give them actually works. Don't ever make your end users compile or even install code. If there's packages you have to load to run your code, put them in a container and make sure they're available, right? I mean, containerized software makes it really easy for end users to consume. And then deploy it on a PaaS platform and deliver it as SaaS instead of having them spin up a machine image and interface with a machine, right? As we've been saying. The other thing is, focus on use cases instead of tests and benchmarks. When you actually give the example of how to use the code, don't put some arbitrary benchmark there as the example. Pick a real use case, and maybe it's maybe it's one that the scientist is going to look like and say, that's like no one actually does that in terms of just to cure cancer or whatever. But it's a use case they can relate to. And they actually use it to understand, how the code works and to test the code. And then what that also does for the developer is it validates that the code actually works for the reason it's intended to be used, right? So the result of running code should be value, not timings or just kind of solutions. It has to actually provide value to the user. Otherwise, there's no reason to actually run the code. And your code should be a platform for innovation, not innovation to the platform, right? Unleash the science to actually, kind of make the next breakthrough with your code instead of figuring out how you're going to make your code even prettier next time, or even more capable or more functional, or adding more extensions that those scientists may not even ever use and much less necessarily understand how to use. Right? So if you just take one thing away from all this, it's that accelerated software and compute is the key to innovation for all mankind. So I lied, there's a couple more things that I want you to take away from this. One is serverless workflows, not instances or machine images. Stop having people spin up instances to run your code. Start looking for platforms as a service products like JARVICE, like the Nimbix Cloud, that can enable you to take your containers and just deploy them with a very straightforward interface for end users. Design for the 80%. Design for the 80% and enable extensibility for that other 20%. But make sure the 80% use case actually works every time. And maybe that's 3 or 4 or 5 use cases, but figure out what the 80% actually is. And remember that it's not about your code, it's actually what gets done. So thanks very much. I just want to add that we're going to hear a lot of interesting topics today. Obviously, accelerated computing, front and center. but you're going to hear a lot of machine learning, a lot of data science, and obviously, software development. So if anyone has any questions, Steven's going to walk around with a microphone and be happy to try to answer them for you.
Any questions?
Thanks, Leo. It was very good presentation and I think thought-provoking. One, as you were talking, an idea that came to me that for compute coming to a cloud model is sort of natural, which is kind of where we want to be. But I somehow get at times asked and held back about data ownership, and so when we are now pinning all this on data, could you comment on it or give us your thoughts on how to allow multi-tenant environments where people need those kind of computes, but they are all sort of cagey about bringing their data on?
Yeah, I mean, I think there's many answers to that, obviously. One is to kind of the most sort of drop-in solution is to choose a cloud provider that can take your data and segregate it and make it available to you without locking you into a dedicated solution. Which is actually what we do at Nimbix. We actually have customers who have their, in some cases they have private data, but they use public compute for it. And the platform actually orchestrates all the, the segregation around that. The second thing is anonymize the data before you process it, which is very common in obviously in life sciences, right? I mean, it's not important what the patient's name and age and address is. It's important what their, what their medical history is. And obviously HIPAA has all kinds of constraints around that, but the point is, anonymize the data to boil it down, reduce it to what's actually important. So maybe you don't do your filtering in the cloud. Maybe the result of your filtering is actually streamed up to your analytics platform in the cloud, right? So the hybrid solution might be the answer there. The third thing, well, I'll say two more things. The third thing is that a lot of data actually originates in the public cloud now, especially reference data, right? It's not, private data is not going away ever. I mean, there's value in data, but the fourth thing I'll say is that the value is shifting from what's in the data to what the data actually tells us. And that's where the analytics are much more valuable than the data itself. And that data set, I think that the era of data sets existing in isolation is going to come to an end. That, your private data is interesting to you, but the benefit, the kind of the analytics around that are not interesting until you collate all this other data in the world to it. So kind of the value of private data is going to start shifting into kind of the IP around analytics. Right? So that's my kind of four-part take on that. You're welcome.
Any other questions?
Thank you. Hello, Leo. Thank you very much for the presentation. I completely agree with all those the things that you pointed out about serverless computing and focusing on the person. I was wondering if you could tell a little bit more about how you isolate your containers on the bare level. Do you see any security issues when you run multiple workloads from different users that you cannot trust?
Right. So the answer is, no, we don't see any vulnerabilities. We've worked very hard. We've been containerizing workflows for almost 5 years, and we've run countless enterprise workflows in our cloud. But even more fundamental to that is that most of our environments are there's only one workload running on a physical node at a time. Because again, remember that in the high performance space, we have no problem with utilization. It's not like in the commodity space where it's like, well, I only want to pay for 1/20th of a server because I'll never use a full server. Here, it's no issue. I mean, using the full capabilities of the machine is kind of the standard community that we cater to, whether it's accelerated or not accelerated. It's traditional HPC. So most of our workflows actually run as many physical machines, dynamically organized together, and that's the only tenant actually running on those machines at that time. In the case where there's sort of fractional use of machines, which makes a little bit more sense when you're using, kind of GPU platforms like the Minsky, for example, from IBM, or the PGX from NVIDIA, where you have a bunch of, and maybe you have code that you only need one GPU for, so you want to actually containerize or fractionalize. We've worked very hard over the last 5 years. We have IP around it, as well as unique technologies that isolate workloads from end users, and we have also monitoring in place to ensure that intrusions don't actually happen. So I would say that it's at this point, for most use cases, it's at least as isolated as virtual machines from our experience.
Any other questions?
Touch on open source. So what role does open source overlap with?
Sure,
software?
huge. My mentor liked to quote all the time. I don't know who originated the quote, but we stand on the shoulders of giants, right? I mean, we are here today because of Linux, because of a lot of the open source tech. Obviously, most of the frameworks are open source, etc. And that's just it's a beautiful example of exactly what I said about data being applied to code. The code itself is, with all due respect to all of us in this room, and myself included, it's not that interesting. It's really about how we take that code and apply it to problems, right? And that's where the real value of software has shifted. It's no longer about protecting that beautiful loop that you wrote. It's about now kind of designing analytics that incorporate many different types of code and produce amazing results based on the data they're ingesting. So, but I think it would be very difficult for any of us to exist in this form, certainly for the cloud to exist. I mean, just think about, can you think of any other than maybe, I don't know, other than Azure, can anyone think of any sort of closed source clouds out there that are big and popular? I can't, and it's true. I mean, people have closed source technologies in their clouds, but Zen Server powers Amazon. Google's got using KVM and using other technologies. Obviously, we use Linux. Everybody uses Linux. So it'd be very difficult for us to exist in the state that we exist today. It would really be more like the 1970s, where we would walk into the office, sit down at the terminal, and code all day. And I wasn't alive through all the 1970s, but that's kind of how I envisioned that era, right? And even the 80s to a great extent. So no, I think open source is critical, and we probably don't honor it enough. So we just kind of assume it's there. But on the other hand, many more people contribute to open source today than maybe 10 or 20 years ago. So I would say that, in fact, even at Nimbix, I mean, we have just tons of code on GitHub now, and things that once we started making our sort of container ingest technology more sort of Docker friendly, let's say, we started putting a lot of repositories on GitHub that people can just look at things that we made in the past and get protected. And it's really come down to like, well, is that even worth protecting? It's just not that interesting, right? So that's my answer.
Any other questions?
All right. Thanks, everybody.